And, and with that, I'm jumping the gun. And with that, I'd like to introduce to you David Yoxtheimer. David, it's a pleasure to have you. It's a joy working with you. Dave's a hydrogeologist at Penn State. He's instrumental in the programs that are developed at the Marcellus Center for outreach and research. And today we'll be talking about the flowback and produced water management. David, thank you for being here. We really appreciate it. We appreciate your expertise, and I'm looking forward to this presentation. So thank you, and I'm going to turn it over to you. I'll stop sharing my screen, and it'll be all yours.
Okay, great. Well, thank you, John. While we transition here, it's nice to see people from all around North America. Looks like a lot of you have much nicer weather than we do here in central Pennsylvania. Pull this up here. Although I don't really know what the weather's like outside. It's always 70 degrees in my house, and I haven't been out that much. So, but I hope everybody's doing well during these extraordinary times. And without further ado, here we go. Okay. So again, I'm Dave Yoxtheimer. I'm a hydrogeologist at Penn State's Marcellus Center for Outreach and Research. And so we're, work as part of the TOPCORP program. So I've been fortunate to, travel some of your states and do some of the trainings there, whether it's in Colorado or California or Texas. And at the Marcellus Center, we're a little bit unique in that you'll notice in our name, it's the Center for Outreach and Research. So we do a couple of things. We try to facilitate the research that that the industry can use to make operations safer, increase the recovery efficiency of hydrocarbons, things of that sort. But then we also try to take that research that we conduct on campus and disseminate that to the various stakeholders out there. So whether that be the regulatory community, the industry itself, environmental groups, landowners, you name it. So we just try to get the best information available in folks' hands so they can make well-informed decisions. So that's a little bit about the center. Again, I kind of backed my way into the shale gas industry as a hydrogeologist. I really honestly didn't have much, if any, oil and gas development experience. But when the Marcellus took off here in Pennsylvania and in the mid to late 2000s, I was still in the consulting world and began to work with some of the Marcellus companies here to get them the water they needed for their frac jobs. And then that started to develop into doing more full service engineering. So our team at the time that I was working with, we kind of reinvented ourselves a little bit. And then ultimately we started to get into the flowback and produced fluids management part of the sector. So we were actually one of the company I was with at the time, ARN Group, was one of the early movers on the need for produced fluids management. We developed mobile treatment technologies and things of that sort. So I kind of had some frontline experience, and then I joined Penn State about 10 years ago, where I get to still study some of the industry trends and share that information, which I'm going to do here with you today. Just sort of some big picture slides here. When we're talking about shale energy management, we need to think about, or development, we need to think about water management. And, whether that's from, initially acquiring the water, and that's going to, these practices vary all across the US and North America and the world. So you really have to pull from, the available water resources that you have. And so here in, northeastern part of the US and the Appalachian Basin, we've got lots of surface water. So we see the majority of the water used for hydraulic fracturing is from surface water sources. But I know if you go down to the, southwest part of the country, you get more groundwater use. So that's important, where you're getting your water from, how much you're using, and then how you're going to get that to the site. A lot of different options out there depending on the available infrastructure. Obviously, there's lots of trucking of fluids, both the fresh water to the sites and the produced fluids to, whether it be disposal wells or treatment facilities. So there's lots of water transfer going on. I think the industry in the last, 5+ years really started to see the light as far as being able to pipe fluids. Again, whether that's fresh water or brine, which reduces the truck traffic and the associated issues there, but also tends to be a more cost-effective practice over the long term. So once you get the fluids on site, you're going to blend in your frac fluid additives, inject the fluids down into the shale, and then you're going to have, over the course of time, a return of those fluids that have been injected, a portion of those fluids that have been injected down into the shale, along with any native or connate water that was in the shale. And so that's where we start to get into the produced water or produced fluids management and ultimately disposal or recycling. So that'll be kind of the focus of today. But that's just, again, big picture. This is another way of kind of looking at the process as far as the water cycle goes, and you're bringing in water, blending it with the chemicals, injecting it, into the hydrocarbon bearing formation, the shale, and then you're going to get some percentage of your fluids that you originally injected down in there. You're going to get a percent of that volume back, and initially we consider that to be flowback. And then as time goes on and the well's actually commercially producing oil or gas or natural gas liquid, you're going to get produced fluids along with. And so it's really how do we manage those fluids in a environmentally sustainable manner that's also cost effective for the industry. So we'll explore some of those options out there. So what are flowback versus produced fluids? And I just kind of touched on that. But again, when we're fracturing a well, we know that this is a fairly water intensive practice. And let's just say we're going to use 10 million gallons of fracturing fluid to fracture a well, we'll say has a lateral length of 5,000 feet. So we're going to be injecting about 2 million gallons for every 1,000 feet, or about 2,000 gallons per foot on average into the shale. So as you inject those fluids during the fracturing process, which may take the course of a week or so to fracture the well, once you're completed with your fracturing, a portion of those fluids and you begin to flow back the well, a portion of those fluids that you injected down in there are going to return back. And that volume varies. Here in the Marcellus in Pennsylvania, we'll get typically between 5 to 10% of the fluids that we injected back out of the well initially. And then again, as you begin to produce economic volumes of hydrocarbons, you're going to continue to get fluids returning up the wellbore, and they're collectively known as produced fluids. So sometimes those terms get thrown back and forth, but some people do use a distinction, and that's typically the distinction. The flowback's that initial surge of fluids you get back before the well's actually producing, and then the produced fluids are what return back as the well's actually actively producing hydrocarbons. So just kind of gives a sense of the relative costs of all the different phases. So I throw this up here. If we have a $10 million well, between the cost to drill it and fracture it, the completion fluids and the flowback, basically your water management, is based on this study, is about 12%. So you could be looking at, on a $10 million well, in excess of $1 million in fluids management. So it's not an insignificant cost, and so finding ways to do that as efficiently and cost effectively as possible are going to bring down the operational costs of developing shale energy, and with the prices of oil and gas pretty depressed right now, you know, any of those efficiencies are going to be important from an economic standpoint. You know, we're talking to a, you know, pretty geographically dispersed audience here today. And so different basins, there's different approaches. And, you know, here in the Marcellus, you know, these numbers are a few years old. But if we're going to, you know, a few years ago, the average frac job was, you know, somewhere around 5 million gallons of fluids, most of which is surface water. When you think about, you know, overall where the fluids are coming from, some of it might be groundwater. We do use some municipal sources that, you know, originate from groundwater. But then we also recycle the flowback and produced fluids at a pretty high rate. And I'll get into the specifics on that a little bit later. So you could have a, you know, variety of water sources here in Pennsylvania, but the majority of it's coming from surface water sources. And you compare and contrast that to, say, the Barnett Shale. You're using a similar amount of water, but you can see there's a lot more groundwater used in addition to the surface water, so that's about an even split, and then a little bit of recycling of flowback and produced fluids, but not so much. And so if we move to the other side of the equation here, you know, in the Marcellus, the volume of return fluids is relatively low. Again, we'll get, you know, maybe 5 to 10% of the fluids injected down into the shale back initially as flowback, and then we'll continue to return fluids over the course of the well's productive life. So maybe over the course of, in this case, we're saying 10 years, we might get, you know, 30 or more % of the fluids back, but the vast majority of the fluids stay down in the shale, which is relatively dry and does have, you know, some absorptive capacity. Whereas in contrast, down in the Barnett, you get almost all of your fluids back over you know, just a few years. So you've got a lot more fluids to return fluids to manage in, you know, the Barnett and a lot of these other shale plays. So trying to manage those fluids, larger volumes of these fluids, can be challenging. And many other states have a fairly robust network of Class 2D disposal wells. So that's often the most cost-effective method to dispose or manage of these fluids. Whereas here in Pennsylvania, we have a handful of operating Class 2 wells, so really not a lot of disposal well capacity. So again, you know, each shale play is going to be different on how the fluids are managed from the time you source them out of a, you know, fresh water source to the time you're disposing of them, whether that's through treatment, disposal wells, or even recycling where you can. So this is a slide that just kind of shows the relative gas production, and I apologize, these are kind of in awkward units. So we're looking at millions of cubic meters in gas production, oil production, and the basically flowback and produced fluids. But the actual absolute numbers don't matter so much. What we're really kind of interested in here is looking at, you know, the return fluids that you get back, and what that means for long-term management of those fluids. So in this case, this goes up through 2016, and in the Permian Basin, you know, you get a relatively low gas production, but you do get, you know, relatively high, you know, oil and liquids production. But then your return fluid volumes are relatively high. So you're getting, you know, a lot more return fluids per unit of hydrocarbon produced, whereas in, say, you know, the Marcellus, for instance, or even, you know, the Haynesville, some of these dry gas plays, you know, you get, you know, pretty decent gas production, but not a lot of flowback or return fluids to manage. And so this kind of same study kind of looks at it a little bit differently. This is looking at, you know, how much, you know, the ratio of your return fluids compared to your original water use. So for instance, if you're at, 1 here, that means basically everything you're putting down the hole is coming back up. And if you're above 1, you're actually getting a surplus of, fluids back, more than you actually put down there. So again, the Permian, based on this study, you can get, on the order of 2, 3, 4 times more fluids than you injected down there in the first place. But say in the Marcellus, you're getting more like, as we said earlier, 20, 30, maybe 40% of the fluids over the life of a well. So that was, more on the the upper chart here is more of the gas side of it, and down here in the bottom we're looking at the oil side of it. But basically the same trend there as well. So basically your water wet shales tend to produce more flowback and produced fluids. They just don't have as much absorptive capacity. The hydrocarbons kind of repel the water back out, whereas the dry gas plays, again, can absorb more of that water and actually draw it in with capillary forces. So just an example of water and oil recovery, and this is from the Bakken. And so you've got cumulative flowback here on the left y-axis, and you have the percent oil cut, the fluids that are coming back, how much is oil versus water or brine. And so what we're showing here is over the course of time, you're getting a higher and higher oil cut. And this is just over the course of just a couple days after flowback, but basically go from 0 to somewhere between 60 and 70% oil in the liquid. And then when you think about how much fluid you injected versus how much you get back, the flow back in the first 24 hours, you get about 12%. And then overall during this 2-day period, they got about 17% of the fluids injected down in there back as flow back, just to, again, give you a relative sense of the volumes of fluids involved. When we think about the quality of the flow back and produced fluids, this is an example from, across many of the western basins, both conventional and unconventional formations. But even from play to play or formation to formation, you can have quite a bit of variation in your total dissolved solids or TDS concentration. So if we look at, for instance, the Williston Basin, you may see anywhere from 1,000 milligrams per liter to 300,000 plus milligrams per liter of total dissolved solids in the produced fluid. So generally speaking, your early time flowback TDS concentrations are going to be low. The fluids have not been in the formation for very long, don't have a chance to dissolve out salts and other metals down there. But over the course of time, and I'll show you, just an example graph, is you have more water or fluid rock interaction, you're going to dissolve out more of the dissolved solids, and they're going to come back up as produced fluid. So generally your TDS levels increase over the course of time until they start to reach some sort of equilibrium. And so again, this is just a little bit of a different way of looking at, in the case of the Bakken Shale, the produced fluids, salinity. Again, your parts per million in salinity here. And so early during the flowback, maybe you're in, the 50 to 60,000 parts per million range, but that could easily double over the course of time. And so that's not an uncommon value to see 200,000, 300,000 milligrams per liter in some of these plays. For instance, the Bakken and the Marcellus are pretty notoriously highly saline, which can make reuse of the fluids more challenging. So there may be some treatment necessary for reuse, or greater additions of fracturing fluid additives to offset any potential interference issues. And so this kind of breaks out, the various ions that cause the high TDS. In this case, again, still looking at the Bakken here. Generally, you're going to have, chlorides kind of driving the TDS levels, and then sodium along with that. And then you may have, calcium, magnesium, iron, some other ions, but typically the salts, sodium chloride, calcium chloride potentially are what's going to drive your TDS with development of these shale formations. This is just an example from the Marcellus, looking at days since well is hydraulically fractured, and looking at the TDS here as the blue line. So again, going from low salinity in the first few days, and then increasing that so that you're in excess of 250,000 milligrams per liter of TDS after roughly 90 days. So generally your volume of flow will drop off over that time, but your salinity is going to increase quite a bit. So you'll have less volume of fluids potentially to deal with, but higher salinity. So how you manage those fluids may actually change over time. Some companies may choose to recycle the early returning fluids because that works better with the frac fluid chemistry, but then dispose of the higher salinity fluids to minimize any of the frac fluid interference with the chemistry of the return fluids. So that kind of covers the chemistry side of it, and then again, based on the chemistry that you're experiencing with your flowback or produced fluids, may dictate on how you end up managing those fluids. I come at this having worked in the Appalachian Basin, especially in Pennsylvania, where the industry does recycle the vast majority of the flowback and produced fluids, whereas in many of the other plays, these fluids are primarily disposed of via disposal wells with very little reuse. But the four basic options out there would be to directly use flowback or produced fluids to fracture another well. So this is fairly efficient in that you really don't have any treatment costs, but you may have increased potential for downhole issues such as plugging, for instance. That would depend on the chemistry of both the shale and the fluids that you're sending back down there. So that's something the industry needs to consider. You may have on-site or field treatment in reuse. So you do have some level of treatment in the field, which minimizes any downhole scaling issues, but you're going to have some cost associated with that. Another option would be to truck any return fluids to a centralized treatment plant. We have on the order of 20 treatment plants throughout Pennsylvania, and those plants were very busy 7, 8, 9 years ago. But as the industry realized they could recycle the fluids out in the field at lower cost without production impediments, you've seen a lot more of the fluids recycled out in the field. So there's not as much trucking to these centralized plants, and their capacity is they have a lot more treatment capacity because they're not used as much. And then ultimately you could have off-site treatment and disposal. So no recycling whatsoever, which again, I know occurs in many shale plays where you have an abundant capacity of disposal wells, and that ends up being a fairly cost-effective solution to basically inject the fluids back down into the earth where they came from. So depending on your strategy, if you are going to treat for recycling, there would be some considerations there based on what kind of treatment technology you're looking at. You'd want to have a technology that has a high recovery of the fluids, so you're minimizing your waste volume and the associated disposal. It removes the contaminants that you're concerned about, whether that's chlorides, for instance, or maybe it's total suspended solids. And that's something I should maybe mention is, we've seen a complete evolution of how the industry manages fluids here in the Marcellus, where when the Marcellus originally was being developed in the mid-2000s and even up through, the early 2010s, a lot of companies were using primarily fresh water, and it wasn't around till 2010 where companies started to see that recycling could be done with at lower cost and not affect well production. So then you started to see a lot more recycling of these produced fluids occurring. But on the treatment side of things, you don't see a lot of advanced treatment. Really, the industry's kind of focused on removing, total suspended solids to minimize sort of the physical plugging of any fractures versus trying to remove dissolved constituents like chlorides or calcium or magnesium or barium or strontium, which could be, which are common scalants out in the field, potential scalants. But any treatment, basically you want it to be simple and low cost. And it also needs to be flexible. We do see quite a bit of modular treatment, in-field treatment, trailer mounted type systems that can be brought in, handle the fluids when they're there, and then move on to the next site. So again, there's no single silver bullet here. You kind of have to tailor your treatment and management scheme based on, your particular needs. When we do think about recycling of the fluids, there are a lot of tools in the toolbox. Again, they're not all being used nowadays. We do see, a lot of filter socks out there in a lot of the plays to cost effectively remove total suspended solids. We did have quite a bit of chemical precipitation technologies out there to remove potential scalants out of the fluids for recycling. You did see, on some level, electrocoagulation be used to also remove scalants, but not nearly as much as, say, chemical precipitation. And then on the sort of advanced treatment side of things, if you want to remove things like salts, you're going to have to start looking at some sort of evaporative technology to basically create a distillate that separates the dissolved salts from the water. Reverse osmosis generally can't handle more than, say, 40,000 milligrams per liter of total dissolved solids. So it doesn't really work in too many of the shale plays. And that's again where the evaporative or thermal technologies come into play. You could potentially use filtration, but again, it doesn't get a lot of attention out there. Kind of has an upper limit on the TDS it can handle. Oxidation's listed here. Again, that's really not going to remove anything, but it helps balance out the chemistry a little bit. And then when we think about the relative costs, something simple like a filter sock might be less than $2 or maybe even less than a barrel per dollar per barrel. But some of the advanced treatment technologies, could be in excess of $10 per barrel, which, might not be economic for a lot of companies out there. To treat these fluids for recycling, every company may have, or every reservoir engineer may have a different philosophy on what they feel the formation can handle without having, again, adverse impacts to production. So generally we see the total dissolved solids be something less than 50,000 parts per million. And then, you know, you can see there's a whole host of other parameters of interest, and this is based on an industry-wide survey. So, you know, things like hardness, you know, barium, strontium, iron, manganese, we'd mentioned, calcium, magnesium, sulfates, total suspended solids. You can see the desired treatment levels there when sending these fluids back downhole during recycling of flowback. You know, so I kind of covered a couple of the scalant removal technologies. We talked about chemical precipitation, which is very effective. It's, you know, a very conventional technology, been around for a long time. Electrocoagulation's been around. It's not quite as efficient at removing some of the scalants, but it does lend itself maybe to being used in the field a little bit more. Again, it's not a super common technology out there and can be kind of finicky. But when we think about, you know, a scalant removal treatment scheme and just the sort of the treatment process, you're going to bring the fluids in. Often they'll run through a sedimentation tank to drop out the heavier fraction of any of the solids in there. You may add in a coagulant, allow that to take effect and flocculate out your scalants, run through a clarifier. And then ultimately you're going to end up with quite a bit of sludge, wastewater treatment sludge that typically needs to go to a landfill. So there is, you know, now you've created a solid waste management issue that you need to deal with. And depending on the nature of the radionuclide concentrations in your flowback and produced fluids, you can have quite a bit of naturally occurring radioactive material in here, which, you know, some landfills may not be willing to accept. So again, you kind of have to tailor your water management scheme to not only just the physics of it, but then also the regulatory framework within which, you know, an operator's operating in. I already kind of talked about the desal technologies out there. We do see, you know, thermal distillation, such as mechanical vapor recompressions used pretty commonly. It's more fairly energy efficient. The membrane systems, as I had mentioned, aren't very useful in many of the shale plays because the TDS of the flowback and produced fluids is too high. Where you do have higher TDS flowback and produced fluids, really you're starting to, like I said, get into evaporative technologies or even potentially crystallizers. Perhaps membrane distillation. I'm not an expert in that, but as I understand, it's a fairly expensive operation. So you don't see, you know, beyond evaporators and maybe crystallizers, you really don't see a whole lot of other high TDS treatment technologies being used out there. We do see, you know, quite a few field treatment technologies out there. So basically scaling the technology. So again, it can be brought in on a trailer and taken out into the field. And what that does is it minimizes your trucking costs, which can be, you know, quite significant, again, along with any of the hazards, roadway hazards with trucking those fluids. So, you know, it ends up that field treatment can be cost effective, especially as technologies and efficiencies improve. And, you know, of the fluids that are recycled here in the Marcellus in Pennsylvania, about 2/3 of that recycling occurs in the field. So as I'd mentioned, there's quite a lot of capacity in centralized treatment plants, but the fluids, you know, just aren't making it there because it's, you know, generally more cost effective to manage them out in the field. Just to give you a sense of, you know, some of the emerging technologies out there that could be used, forced crystallization, using waste heat from compressor stations, for instance. We have at least one operator who's been using, you know, the waste heat coming off of compressors and using that to, in essence, distill the waters so that they can recycle. So it's basically a free heat source, which greatly reduces the cost there. So there are some innovative things that companies may be able to do internally. Just to give you a sort of a breakdown, an example in Pennsylvania here, this is kind of hot off the presses here, looking at 2019 produced fluids management in Pennsylvania. For every million cubic feet of gas, we're getting right now around 9 barrels of produced fluids. In Pennsylvania, you had 6.8 trillion cubic feet of gas produced in 2019. And as I show down here, a total of 61.2 million barrels of flowback and produced fluid. So if you do this math here, divide the total million of total volume of barrels of fluids generated divided by the gas produced, you basically end up at 9 barrels of produced, basically flowback and produced fluids for every million cubic feet of gas. So you think about if a well's producing, let's just say 10 million cubic feet per day, you're going to have on average about 90 barrels of fluids to manage just from that one day of production. Again, the second bullet here relays the point that Pennsylvania recycles a lot of their flowback and produced fluids. We've been doing that for nearly a decade now. In last year alone, they recycled 85% of their flowback and produced fluids. So basically 52.3 million barrels out of the 61.2 million barrels generated were recycled, and about 2/3 of that recycling, as I'd said, occurs out in the field. The other 1/3 would involve taking it to the centralized treatment plants. Disposal wells handled just about 8% of the total fluids, or about 4.7 million barrels. I said earlier, we don't have many disposal wells in Pennsylvania, so a lot of the fluids are sent to disposal wells in Ohio to the tune of 90% of the 4.7 million barrels of fluids generated that went to disposal wells in Ohio. So there's a lot of trucking associated with that at significant cost, depending on where in Pennsylvania you are with respect to where the disposal wells in Ohio are. You may be looking at in excess of $15 per barrel to haul fluids to Ohio's disposal well. So it gets pretty expensive. So you can start to see why in Pennsylvania, recycling is a much more common practice than many other, basically all other shale plays in the U.S. This is a study that I worked on with Katie Schmid from the Pennsylvania Bureau of Geological Survey. I saw Katie ping in here, so I know she's out there. Hi, Katie. So we've been getting a lot of mileage out of this one. This is a few years old now, but really just gives you a sense of when we think about how much water we're using to fracture a well, what percent is produced fluids. So it's somewhere between 20 to 25%. Historically, we are starting to see that number creep up nowadays. So in some cases, operators may be using 40 or 50% flowback and produced fluids in their fluid frac mix to help cost effectively, manage that volume of fluid. So that prevents a couple of things: the need for disposal, or at least it delays that need, and it also minimizes the need for fresh water use. So there is some environmental benefits there for sure. When we think about brine disposal well siting, I know you can go down to Texas, and there's an excess of 8,000 disposal wells, and if you go up to the Bakken in North Dakota, there's on the order of 400 disposal wells. So there's a lot of disposal infrastructure already in place. But when you go to site a new disposal well or retrofit an existing, say, depleted gas well into a disposal well, you need to look at some both geologic characteristics, but also, surface land use. So ideally, a disposal well would be sited away from population centers. Here in Pennsylvania, these have become, a very hot topic, highly debated, lots of public opposition. Nobody wants a disposal well, near where they live. They don't want to see the trucks coming through their town. So this has really set up a, kind of a legal battleground for disposal wells. But if you can find, the right surface location away from population centers, so as to minimize that disturbance, in combination with the right geologic setting where you have sufficient permeability in the injection reservoir, as well as, confining layers, prevent, any unwanted migration of fluids upward, as well as, a lack of faulting, so as to minimize any, induced seismicity issues. Those are the kinds of geologic characteristics you'll need to take into consideration. Seismic monitorings, fairly common with disposal wells now. We have the Pennsylvania Seismic Network in Pennsylvania, which is 30 stations across the state that are designed to be able to pick up any, seismic events greater than 2.0 magnitude. And in addition, if you're an operator of a disposal well in Pennsylvania, you need to have, your own seismic station associated with your well, in addition to the state's network. Long-term well maintenance is necessary. Mechanical integrity testing to make sure the well has sufficient integrity, so there's no loss of fluids into undesired zones. And as I'd mentioned, these can be very difficult to get. Ultimately, you can get your permit, but to have your ability to operate and to avoid the legal battles is pretty tough out there. So we've seen, wells take years until they can finally operate, from the time they start to permit till the time they can operate. And, even recently, we've seen basically well permits rescinded because the state does not want to fight the battle set up by the local communities. So again, it's kind of an interesting sphere in the legal world right now, especially here in Pennsylvania. When we think about, injection well capacity, again, we have lots of conventional wells here in Pennsylvania. Many of them have been drilled into the Oriskany Sandstone, which is a fairly common injection reservoir for disposal wells. And so you need to look at, well, just what volume of fluids can I inject down in there and at what pressures. And so if you just look at just from the porosity of the bedrock, basically the pore or the secondary, the primary porosity between the, say in this case, sand grains, in addition to any fracture porosity. This is just an example. But if you had a well that was drilled into a zone that had an effective porosity of 4%, it's a 50-foot thick pay zone, and the drainage area for that field, it was 40 acres or assumed to be 40 acres, then a typical injection well in this particular sandstone could ultimately accommodate about 620,000 barrels or about 26 million gallons before just filling the primary porosity down there. So again, this just kind of starts to give you a sense of what volume of fluid you could inject just to fill the porosity up. That doesn't really take into account being able to inject at pressure, which could in theory allow you to inject quite a bit more. So this is just an example in months on the x-axis and injection pressure on the y-axis. So as you're injecting fluids down into a disposal well, you're going to be limited by basically the fracturing pressure of the formation you're injecting into. And generally speaking, you can't exceed 80% of the fracturing pressure. So if the fracturing pressure is assumed to be, say, 5,000 PSI in a given formation, you're not going to be able to inject fluids down into that formation at greater than 4,000 PSI to avoid any fracturing. So basically, just the gist of this plot is to show how the pressure builds up down in the formation over the course of time. It builds up rapidly in the first several years and, you know, starts to kind of plateau out over the course of time. And, you know, you can read the assumptions. So these are all the parameters you need to consider. You can plug it into this equation, and that'll give you a sense of the pressure. So you can kind of model this in advance. But if you're injecting 1,000 barrels per day for 20 years, you know, your pressure is going to be around, you know, 3,400 PSI, which is below the fracturing pressure, but above 80% of the, which is below the fracturing pressure, but above the 80% of the fracturing pressure. So you'd already be too high in this particular case. You would have had to have stopped injection previously. All right, so just a little bit, I know we covered a lot of territory there, but that was sort of the soup to nuts on produced fluids management. You know, really what you're looking at is needing to have environmentally sound, cost-effective fluids management solutions. You know, recycling, which again does not occur at significant levels in many shale plays, can actually be very cost-effective with, you know, some of the environmental benefits we discussed: less fresh water, less need for disposal, and the associated issues there. You know, there's a whole host of treatment technologies out there. Finding the right fit for your application is what you're going to need to do there. But ultimately, you know, these plays are long-term plays, so you really need to be looking, you know, at long-term strategies. You know, here in Pennsylvania, we're reaching a point where we're producing, you know, nearly 7 trillion cubic feet of gas per year, generating, you know, 60+ million barrels of fluids per year. And that's great when we can recycle 85% of those fluids. But now as we're, you know, starting to see activity start to drop off, there's not as much fracturing. Now suddenly you don't have as much of a window to recycle those fluids. So, you know, treatment schemes that allow disposal or disposal wells themselves are going to need to become a much more significant part of our fluids management portfolio in our part of the world, and, you know, again, in others as well. So with that, if there's any questions, I'd be more than happy to try to address them. Thank you very much.
David, thank you for the extremely fascinating, and wow, you have a lot of information there. And we've already had some requests that want to see it later on. So you must have hit the ball pretty hard here for us. So we appreciate that. And there are some questions. I don't know if you can see the Q&A pod, Dave. I scooped the question out of the chat pod. If you don't mind, if I just sling it to you, and then maybe we can go to the Q&A pod. But this was, excuse me, what's the difference, or what is different about the Permian Basin that results in a higher flowback volume than the Marcellus Basin?
Yeah, I've not really studied the Permian in great detail, but, you know, there's a few factors that would affect that. One, you just have a lot of water in the shale in the first place. So when you start to produce that shale, you're going to start to draw in water that's naturally occurring in the formation. So, and given that it's already fairly wet, you know, the fluids that you're injecting down into the shale just don't have anywhere to go. So you're going to get, you know, the vast majority of your fracturing fluids back, along with the fluids that are already down there in the Permian shale. So that would really be, why you get more of those fluids. Here in the Marcellus, the formation is pretty dry. So again, it kind of acts like a sponge and can absorb much more of the fluids and kind of pulls them in. The capillary forces draw it in, and once they're drawn in there, they really don't have anywhere to go.
Okay, thank you, David. And did you say that you could see the Q&A pod?
Yeah, I can pull them up here, I think.
Okay, if you can, it's probably easier for you to read them and assimilate that in your mind to answer than to me. And I see another question I'll pull from the chat pod. If you want to start with the first question, or with a question there in the Q&A pod.
Okay, so I'm looking at the Q&A here. So I got Pat Shreves asking, would saline water be optimal for the frac in shale versus fresh water for stabilization purposes? And yeah, generally, if you've got clays in your shale that have a lot of potential to swell, then oftentimes they'll add in a clay stabilizer to minimize that swelling of the clay, which tends to sort of pinch off the fractures that you're trying to open up. And so salt water can also be used. So that is one advantage for sure. So that really comes down to understanding the the mineralogy of the shale you're working in, along with your frac fluid chemistry, to make sure they're compatible. And then Cindy Beeler's asking if I'm aware of studies or measurements of air emissions from the handling of produced waters. There is some info out there. I know certainly, when you're working in a, wet gas or liquids environment, you have a lot more potential for, the natural gas liquids to volatilize. So you can definitely have more issues there as compared to, say, the dry gas play where you've got, methane, but that's about what all you have. Now you could have, some of the, any organics or volatiles in the frac fluids themselves, could result in some air emissions. But the way they, rather than have open top tanks and things like that, you can do a better job of controlling those emissions with closed top vessels, we'll say. And then Justin Abbott's asking about chemistry difference in produced or flowback water, and any differences which determines whether the water is reused in the field, removed from the field for treatment, or removed for disposal. And yeah, definitely. At some point, if the TDS on the fluids is so high that it's going to interfere with, say, your friction reducers, company's going to have to, make some decisions as to whether it makes more sense to add, higher volumes of, say, friction reducers or other additives to offset any interference or not. So again, as I mentioned earlier, the flowback generally lends itself to being reused pretty easily because the TDS is lower. Whereas, produced fluids that have higher TDS numbers, might be more of a candidate for some sort of treatment and or disposal. So yeah, the chemistry matters there for sure. And then Tricia Pfeiffer's asking about what is being done with the salt being generated. And if you'll notice in my picture here, this is the salt being generated from a crystallizer at a facility here in Pennsylvania. In this case, this company actually has approval to use, basically create a beneficial co-product, basically salts that can be used for basically water softeners and the like, which may surprise some. But generally speaking, this is where disposal wells, you can send the highly saline fluids back into the formation. So what operators don't want to do is create lots of salt because it doesn't really lend itself for solid waste disposal at landfills and things like that. I know some operators have come up with a way to, in essence, mix the salt in with, in essence, like a Portland cement. So you end up with a concrete that has, low solubility, so that the salts don't leach back out. But again, that's not exactly ideal. So, but there are strategies out there, but you can, the salts can be used in the chlor-alkali industry. So there are some industrial applications as well. So I think this is where, you need some creativity and some out of the box thinking to figure out the best uses for these salts. Are there any research conducted on the biologics regarding high TDS waters? So I'm assuming you mean, is there microbes and other biological creatures in there? And to a certain degree, yes. You can have, for instance, sulfate reducing bacteria. You can both introduce it into the shale, and it may actually exist in the shale. I know there's a lot of work in that field, but there has been just a little bit, and I can't honestly address the ion exchange, but my hunch would be it's either not real feasible or is cost prohibitive. And then in PA, how did the few UIC wells that have been permitted make it through the process while others have been shot down? And that's coming from Dave Yoxtheimer from DOE. How you doing out there, Dave? It's been a little while. Yeah, so it kind of boils down to local opposition, and where some of these wells have hit a snag is that there wasn't sufficient technical review by the operator, the proposed operator of the well. And so there's a few, chinks in the armor, so to speak, and, they don't get approved. There's really two layers of approval here in Pennsylvania. You've got, these are EPA permitted wells. They have EPA has primacy in Pennsylvania. So EPA may, issue their permit under the Safe Drinking Water Act. And now, our state also has the ability to issue a well permit. And so depending on, I'll say local controversy and the technical arguments is how these wells can be permitted versus not permitted. You do have some communities or municipalities, I should say, may have a home rule charter and may declare disposal wells as illegal. And so that's one way municipalities are putting up roadblocks. And so that has occurred recently here in Pennsylvania. We got T. Wallace asking about the difference between evaporation and crystallization methods. And really on the evaporation side, what we're talking about is reducing, evaporating much of the fluids away, but the technologies are such that you still may have, 20 or 25% of the fluids not basically as reject fluids. And so you have a very highly saline, sort of a super concentrated saline fluid now, which then would go to the disposal well. So what you've done is basically concentrated the brine, versus crystallization. It takes it to the next step and actually reduces that. So you basically end up with salt like you see in the picture here. It's like we're getting to that time here, John. I don't know if we want to stop it at this point, and I'd be happy to answer other questions if you want to, email me directly, but I don't want to overstep my time here. So,
Dave, we appreciate it. I was going to ask you, we are at our time, and on cue, Dana has put up our polls, we'd really appreciate it for you folks that are with us. If you wouldn't mind taking just a moment to go through the couple questions that Dana has put up here, it really helps us. It helps our presenters understand how we're doing and what we might do to make it even better next time. And so if you wouldn't mind filling out the poll questions that Dana's put up, we really would appreciate it. And David, I didn't want to impose on you. I don't know about your time. There does seem to be another question here. We can hold over if you'd like to, if your time allows, but if not, it surely could be answered via email.
Yeah, no, if people want to fill it out, I'm happy to answer the question while we're doing that.
Okay, do you want to go ahead and answer? Is it Trish? I can't see it now, but Trish's.
Yeah.
Pfeiffer.
Trish Pfeiffer. Basically, what analytical testing is being done on the salts. Basically, for the beneficial reuse of those salts, they did have to go through, I believe, the FDA to get approval on that. So I don't know all the details on what level of testing, but I know they had to demonstrate that anything that would, have any sort of toxicity associated with it, things like barium or strontium, naturally occurring radionuclides all have to be removed so that it meets, whatever the salt standards are, which I honestly don't know from an FDA standpoint. But whatever that testing is, they did go through to show that, you can use treatment technologies to, in essence, produce pure salt, sodium chloride. And yeah, so then if the T norm is in the produced, or the norm is in the produced water, it certainly could be possible that it's in the salt, but again, it would depend on the treatment level. So the salt that's going out for, again, beneficial uses, they have to demonstrate that there's, no norm in that salt.
Do you want to tackle the dust suppression question, David?
Yeah, there's one here on radioactivity levels, and I don't have those numbers off the top of my head, but there's certainly naturally occurring, radon, radium-226 and 228 specifically, that can be, relatively, high levels. Our DEP's done some studies to show that there's not significant exposure risks from, normal oil and gas field operations. But again, they're relatively high. Certainly above drinking water standards, I'll put it that way. Yeah, so as far as dust suppression, currently there is no brine reuse for, road spreading in Pennsylvania on either the, conventional side or unconventional side. Really was never allowed on the unconventional side, but, some operators did use it when there was still a little bit of a gray area on that, but that no longer occurs. And currently use of brine for road spreading from the conventional industry is also on hold.
Okay, David.
I should mention here, Tricia, that the salt is not being used for human consumption. So you can still put salt on your French fries. It's going to be okay. Although that has its own set of issues. So.
Oh, and thank you for the health minute. Thank you, David. Thank you very much for that really interesting presentation. We appreciate you taking the time to put that together and be with us today. And we are at the end of the time, and thank you for answering the questions that the participants asked here too. And Dana, thanks for getting that poll, and for you folks that took the time to answer that as well. Hey, if you have time and you'd like to join us this coming Thursday, April 30th, we'll be back here again at 1:30 in the afternoon Eastern. And I hope you've already gotten that webinar announcement already in your email. An agronomist from here at Penn State will talk about infrastructure site reclamation and reestablishment of those disturbed sites. And that's Justin Brackenrich, who will be making that presentation and talking about that and taking questions as well. So if you'd like to join us, please be sure to register. This presentation that David has made today will be available. If you've registered, you're here, you'll receive an email directing you to a link that will have the recorded session in a few days ahead of us here. So thanks again, folks, for joining us. We hope you all have a great rest of the day, and we'll look forward to seeing you again. Thanks again.
Take care, everybody. Thanks.